Okay, let us look at this problem similar to other problems we've done, but I want to make sure that we understand the concept. So when we have circular dynamics, the first thing we have to realize is if the angular path is changing or not. So if they give you rho, means that the path has a constant radius, okay, with respect to your origin. So at a distance r, this being the distance, this r is constant, and actually declare rho, and this particular case is constant at 4,500 meters. Okay, this is very important because that means that you can keep that as a constant. If that's the case, then you follow this expression. The acceleration is the change in velocity with time, so dv dt, and the velocity squared divided by rho. Obviously, the magnitude of the acceleration is the tangential squared and the plus the normal component squared. All right, so this is the first case, which is very simple. The curvature is constant. So they give us a curvature of 4,500 meters. They already give you the velocity, is a function. So you just have to differentiate this. And they're telling you what time or times they want to find the acceleration. So the first thing is that acceleration is going to be the derivative of 1/2 of 0.5 t squared. This is going to be just t, okay, from t0 to t1. So t in this case is 5. Very simple. So 1/2 times 5 squared is the velocity, the acceleration is t. Okay, so for the velocity, it's 1/2 of the time. If it's 1 second, 10 seconds, or 5 seconds in this case, we're going to have 1/2 of 25 is 12.5 meters per second. The acceleration is simply the time. Very simple. In this case is 5 meters per second squared. All right, so in that case, all you need to do is find each component. So we already have the component of the acceleration here, and here we do v squared divided by rho. This is equal to 12.5 squared divided by 4,500. This number is 0.03 meters per second squared. So the acceleration is the square root of 5 squared, which is your t, your derivative of the function. Whichever function they give you, you derive it. It's going to be with respect to t in this constant approach. And then you're going to have plus the value of your normal acceleration. The next case is when your path is varying with respect to your coordinate system. Okay, so if you start from x and y, or you move to a polar coordinate system where you would have an origin, a distance, and an angle with respect to your points. In this case, the angle is going to change with time, and the distance can also change because it's a random movement. This r is going to change at different places. So that is a little more complicated, but all you have to do is follow the equations of the acceleration. The radial component is the second derivative of r with respect to time minus the value of r at that given point, because it's a function, remember this varying with time, times the change of angular displacement squared. That is your radial component. Your angular component is your radial direction evaluated at a given time times the second derivative, this is a derivative of theta with respect to time, plus 2 times the derivative of r with respect to time, times the change of theta with respect to time. All these things are functions. Everything here is a function. So in a case like this, where they give you, let's say, a mechanism like the arm of a robot, or something that is moving in a certain path. Let's get rid of this first. All right, let's say something that is moving in a given path has an angular velocity all these things are the same thing, of 1 radians per second. So it's not very fast. 1 radians per second. So it's moving in a circular path, some type of path, okay? So the second derivative of a number is 0. We already have this and that, which we will need for the equations right here. Those are the same as these. Now r is given, is 0.5 theta. So this function is a part of a function. So at every point, r is given by 0.5 times your theta. So you can integrate this guy, or simply evaluate theta. It's very simple, because if you know that r dot, sorry, you know that r, the radial displacement, is equal to your 0.5 times theta from here, then your theta is r divided by 0.5. So whatever r you have, you can have your theta. At a single point, they're asking you a single point. They can ask you 20, 30 points. You can use MATLAB or something to plot those 30 points. But a single point is when it's at 0.3 meters. And it's very simple, because it's 0.3 divided by 0.5. All right, that is 0.6. Perfect. 0.3 divided by 0.5 is 0.6. So we have theta. Now you have r theta dot dot. So r dot, so r as a function of time is equal to 0.5 theta as a function of time. So if you differentiate this with respect to time, is the constant times this with respect to time. And that's what we have here. R dot equals 0.5 times theta dot. This is right here. And the second derivative is the same. This is a very simple problem that they're giving us. In that case, all you have to do is use those values and find the acceleration. The velocity we already know, because the velocity and the radial components are dot, and we know that r dot at 1 second is, well, or basically at theta. Let me say that again. R dot is equal to 0.5 times theta dot, and theta dot is 1. So r dot is equal to 0.5 times 1. So you can use all your values and just plug them into these equations. You have r, you have theta dot. R is 0.3, is given in the problem, and theta dot is 1. And the same for acceleration. You just plug in all the values into these expressions, and you can get your velocities in your acceleration. This is actually an acceleration.